Hello, welcome to lecture 27 of Game Theory course. This is the last class of week 9. Uh, we have talked about the subgame perfect equilibrium of infinitely repeated game, where the repeated game itself is a kind of prisoner's dilemma kind of game with a dominant strategy equilibrium if that game is played just once. We are gonna think of, and I told you that in those kind of repeated prisoner's dilemma game, if that is repeated finitely, there's only one subgame perfect equilibrium that is keep playing the dominant equilibrium over and over again. If it's infinitely repeated, still keep playing the dominant strategy over and over again is one subgame perfect equilibrium. However, there is another subgame perfect equilibrium that is if the discount factor delta is big enough, in our previous case bigger than half, then they can collude, which the strategy is not a dominant strategy, but they can choose to collude. And then if one of them deviates, betray, then they go to the punishment phase kind of game. Okay. But here I want to give you another example where this kind of collusion is possible when the game is not infinitely repeated, just repeated once or twice. How is that possible? Let's look at this game. It's differently repeated game I named. And if you look at the right upper side, there's only two periods, period 1, period 2. So the Sarah and Jane played this game only a couple of times. What's the difference between from the first case is, and other than they have now 3 strategies, but not only the number of strategies has increased, this game does not have dominant equilibrium, rather than it has only 2 equilibria, pure strategy equilibria, UL and DR. Let's check. When Sarah plays U, Jane plays L, they get 1 and 1. If Sarah changes, wow, it's all 0. Jane changes, it's all 0. As a result, they have no reason to change. Another Nash equilibria, where Sarah play D, Jane play R, they get 3 and 3. If Jane changes, 3 can only become 0 and 0. This 6 is Sarah's payoffs, nothing to do with Jane. So Sarah would rather choose R and get 3 instead of 0 and 0. Jane, Sarah, if changes, 3 become 0 or 0. So they will not change. One thing that we are kind of sorry about Sarah and Jane is 1-1 and 3-3. Oh, by the way, 3-3 is better payoff than 1-1. We call that Pareto improvement because both Sarah and Jane get a better, higher payoff. But then, even from 3 and 3, they can make Pareto improvement to 5-5. Look at 6-0. We cannot say this is necessarily desirable from 3-3 because Sarah gets better from 3 to 6, but Jane gets worse 3 to 0. However, if Sarah and Jane move 3-3 to 5-5, both Sarah improve and Jane improve. That is definitely desirable. The unfortunate thing is this M and C, Sarah choose M, Jane choose C, is not a Nash equilibrium. Why? Sarah can change to D and get 6. Jane can change to R to get 6. So this is very well made example. Okay. So if this game is played twice, the question is, if we think this 5-5 is the payoff from collusion, this kind of collusion can be maintained. In other words, can we prevent Sarah and Jane to change their strategy to get 6 instead of 5 in the first period? The answer is yes. Okay. I'll explain with this table, strategic form. Because in the second period, T2, it's same as the one-shot game. In one-shot game, we don't think it's a repeated game. It's just like playing just the game once. We call that one-shot game. And in this one-shot game, there, as I have explained, we are talking about the last period T2. Okay, T2 itself is a one-shot game. And we have two Nash equilibria in this yellow place. It's very conveniently arranged that the payoff is one is 1 and the other is 3. We can use them as carrot and stick. So in T1, Sarah and Jane behave well. We will give them stick by playing D and R 3-3. But if they behave badly, if they have been a bad girl, then they'll play U and L, they'll get 1 and 1. Even though I said they should be punished, like it's their self-punishment, self-compensation. So their promise is, okay, let's play M and C in T1 and get 5-5. Okay? If you keep the promise, in the second period, we are going to get 3 and 3. However, if you are tempted and get 6, what happened? In the second period, we'll play U and L, whether it was Jane or Sarah, we are going to get 1 and 1. So their promise is itself. But once they promise that in advance, even before T1, if anybody betray, anybody deviate from M and C, U and L will be played and we will get 1 and 1. It cannot be changed because Sarah know that Jane will play L. So if she choose something else, she'll get 0. So play L. U, something like that. If they behave well, play DR, they would not change because if Sarah changed to anything, she will get 0 instead of 3. So it's like pre-arranged self-compensation and self-punishment, depending on whether they keep the promise in T1. Okay? How does that work? If they keep the promise, they get 5 in T1 and 3 in T2. Total would be 8 if there's no discount. Okay? If they deviate, get 6, they get 6 and 1. So if discount factor is small enough, what we can expect? The Sarah and Jane compare 5 plus 3, 8 against 1 plus 6, 6 plus 1, 7. So 8 is bigger than 7 if the discount factor is big enough, almost 1. They would rather choose to keep playing M and C in T1. Okay? So the strategy is play M and C and play DR. But if in T1 anybody deviate and betray, play something else than M and C, then they play UL. And that would be the subgame perfect equilibrium where Sarah and Jane can achieve M and C and payoff 5, even though this is not a one-shot game Nash equilibrium. Okay? I summarize that. If it's not repeated game, that the one-shot game has two pure straight Nash equilibrium, UL, DR, payoff 1 and 3. If a one-shot game has multiple Nash equilibrium like this, even finitely repeated game may achieve the collusion and payoff 5-5 by subgame perfect equilibrium. Okay, so we found out a subgame perfect equilibrium where collusion effect can be achieved even though it's only repeated twice. But by no means that is the only subgame perfect equilibrium of the game. Why not? There are actually a lot of subgame perfect equilibrium. In T1, play UL, T2 play UL. In T1, play DR, T2 play DR. In T1, play UL, in T2 play DR. In T1, play DR, in T2 play UR. Because they are Nash equilibria, playing the Nash equilibrium of the game in each period 1 and 2, that is automatically subgame perfect equilibrium. Because subgame perfect equilibrium is backward induction, or in other words, in every subgame, player are playing the Nash equilibrium. And one-shot game Nash equilibrium automatically satisfy that condition. That's why, other than the subgame perfect equilibrium where in T1 the players get payoff 5, there are 4 additional ones, UL, ULDR, DRUL, DRDR, which is playing the one-shot game Nash equilibrium. If all the players move simultaneously and the game ends instantaneously, we call that one-shot game, okay? I keep saying one-shot game. This is what it means. Like rock, scissors, paper, play just once, that is one-shot game. It doesn't take time, just like they give the rock, scissors, paper at the same moment, and it ends immediately it begins. On the other hand, if it takes any time, like somebody played rock, scissors, paper first and the other, or they do it repeatedly, then we need some time spent for the game to be played. We call that dynamic game. So one-shot game immediately ends. Dynamic game, it takes some time, like period 1, period 2, you move first, you move second, something like that. Okay, that's the word. So in dynamic game, subgame perfect has meaning only for the dynamic game, because backward induction means there's a future and you think from the future to the current period. That automatically means it is dynamic. It takes time for the... So in one-shot game, we don't have to worry about subgame perfect equilibrium. Okay? This was a basic idea, but then maybe I introduced a little bit late. But anyway, that's it. So the collusion of SPE, subgame perfect equilibrium, SPE is what I mean. Exactly what I have explained. If you are you write down this way in the exam, play MC and get 5-5 in T1, then play DR and get 3-3 in T2. However, if either Sarah or Jane deviates in T1, in order to get 6 instead of 5, play UL and get 1-1 in T2. As I said, since the two possible results in T2, DR and UR are both Nash equilibrium of the game, it's guaranteed that the strategy of these two is subgame perfect equilibrium. As I said, collusion following the equilibrium path will give 5 plus 3, 8, but deviate and following the punishment phase would give the player 6 plus 1, which is 7. So if delta is big enough, they would rather choose the equilibrium path rather than the punishment phase non-equilibrium path. wow, if you understand all this, think about it. Like at the end of August, you do not know game theory. Now you understand so much to understand all this. Okay, proud of you. Okay, next. Okay, so it's like we are going to talk about the variations of repeated game. Repeated game is actually very big area field of game theory, especially interestingly, many Japanese economists, game theorists are very interested in this repeated game. So there are many famous Japanese scholars. Okay, I think it has something to do with ijime, like when somebody is not behaving well, the student punish them. Whether, justifiably, not justifiable, that's not good. But anyway, that kind of culture maybe fits, the Japanese fits, this repeated game fits Japanese emotion, I think. But anyway, this is not by Japanese scholar, but there's a boom and recession thing. Okay, Sarah and Jane, they are selling apples. If it's always same, like this bottom one, that's what we have talked about, would be good. But then in economy, somehow there's a boom and recession, good time and bad time. I'm gonna assume that the game we talked about, 100, 100, 200, 200, that is like bad time payoff. In good time, everything doubles. 100 become 200, 300 become 600, 200 become 400. And then, because there's a cycle, okay, this is given from outside, the economy alternate, like one in like T1, it's a boom, T2 recession, T3 boom again, T4 recession kind of. So it's every time it's moving to the boom and recession over and over again. Okay, I mean, I think it's kind of realistic, My question is, if Sarah and Jane collude, once again, I'm telling you collusion is illegal. You should not do that, off the record. It's stupid not to try. But anyway, so you're alternating between boom and recession. And then, in which case Sarah and Jane are more likely to break the collusion and deviate? When is it more likely for the collusion to collapse? Is it the booming period? Is it a recession period? One might say, recession period is the time for the collusion to collapse, because in recession everybody is in a pain and they want to get a little bit more money. They're making 200, they want 300, so they may cheat. Other people say, the booming is period to cheat, because in recession they get only 100 gain from cheating, but here 400, 600. Okay, you are ready to calculate. So let's do it. It is this. Think about in recession. If you keep colluding, okay, now you are getting 200, next 400, 200, 400. That is why 200, 400, 200, 400, on and on and on. If you sum them up, like you have 200, 200 delta square, and 200 delta 4 square, so 200 plus 1 minus delta square, 400 delta, okay? 400, 400 delta power by 3, 400 delta power by 5, 200 power by 2 over 1 minus delta power by 2. Okay, this is if both Sarah and Jane keep the promise and collude. What if they compete? If Sarah cheat and get 300, what happened? 300 next period instead of 400, she will get 200 because now they will compete forever. So 300 instead of 200, then 200, 100, 200, 100. That's the punishment phase we are talking about. So the punishment phase, compete means Sarah or Jane cheat. She gets 300, then 200, 100, 200, with considerably half of 400, 200 they would have gotten if they keep the promises. And if you sum them up, you know this is their payoff. So in recession, if you want to keep Sarah and Jane in the collusion, this collusion payoff should be bigger than this competing payoff, cheating payoff. So condition, this is bigger than or equal to the above one, upper one. Delta would be bigger than, okay, I mean, you learned this algebra, and it needs the algebra knowledge. So ask your younger brother and sister and look at their math books, high school math books. You can calculate. If this downside payoff is bigger than this upside payoff, delta should be, it's like delta square plus something. So like a negative b plus minus root b square minus 4ac over 2a, something like that. You know the formula. If you put it there, delta should be bigger than y equal to root 3 minus 1 over 2, which is about 0.36. Pray to God. I hope my calculation is correct, but this is what I get. So, if my calculation is not correct, let me know through YSEC or something. But I think I'm right. I'm like 70% sure about it. Okay? So that's the case. What's next? In booming period, if they keep collude, this would be you collude 400, 200, 400, 200. As a result, this is 400, 200, 400, 200, and if you sum them up, this would be the payoff. Compete means if you cheat, instead of 400, you got 600, then you got 100, 200, 100, 200, because you are entering the punishment phase. So 600, 100, 200, 100, 200, and this is the payoff. Okay? So now, if you want to maintain the collusion in booming period, this downside payoff should be bigger than this upside payoff. So this is bigger than or equal to this. 400 something is bigger than 600 something. If you calculate, well, it's a little bit more complicated. Delta should be bigger than or equal to root 33 minus 1 over 2. Okay? I mean, I'm just saying it like in 0.5 seconds, but you would need good like 10 minutes, maybe 5 minutes to calculate this. So work it out. I mean, nothing is free. Like you have to try. So, and this is 0.59. Compare this. In the recession, if you want to maintain the collusion, your delta should be bigger than or equal to almost 0.36. In booming, delta should be bigger than or 0.59. What does that mean? You should be much more patient in booming to maintain the collusion. For example, if both Sarah and Jane's delta is like 0.7, it doesn't matter. Whether it's booming or recession, they will collude. But what if Sarah and Jane has delta 0.5 In recession, they will still keep the promise and collude. But in boom, because 0.5 is less than 0.59, they will cheat and compete. So basically, when there's a booming and recession, people should be more patient to maintain the collusion in booming period than recession. In other words, it is more likely to be for the collusion to be breakdown in booming period than recession period. So kind of, the rich children, like rich siblings fighting each other, they are not never friendly each other. On the other hand, the really poor family, they have nothing to fight, so the burdened sisters get along very well, something like that. And because they gain a lot by cheating from 400, 600, 200 gain instead of 100 gain, this booming period is more dangerous. So when you have allies, when you have friends, you should be much more careful. The lesson is in when things are good, okay, than when things are bad. That's what you can see from this example. Okay. So this is the end of lecture 27 and end of week 9. Let's meet at week 10 in the next lecture. Thank you.